many you want. I mean, I understand you've got way too many lectures from Georg over there, so you may decide that you want to rebalance a bit, you know, just saying. I'm Jean-Luc, and I will be telling you things about mixing, in particular, stirring and mixing. So this will be my kind of introductory lecture on the broad mathematical aspects of stirring and mixing. It's a rich field, and it's actually a funny field, stirring and mixing. I mean, geophysical people care a lot about mixing, and engineers care a lot about mixing, chemical engineers in particular. Biologists are now starting to care about mixing, but very few people declare mixing to be their profession, like I do. So I'm one of the few people that has decided to commit and say, this is my field of study. Most people just find mixing an annoyance at some point. They go, well, I need this to be mixed somehow. So the question is, how do you characterize this, and what are the mathematical tools? I'm an applied mathematician now. I grew up as a physicist, but I transitioned like Amit, right? I mean, Amit and I are both pretty poor excuses for physicists in a way, right? Is that right? Where's Amit sitting? I'm sorry. I want to see his face while I insult him. There he is. It's true, right? I mean, we don't get, I don't know. Our advisor is, yeah. I mean, worse than that, we're supposed to be plasma physicists, but I think that's the biggest. That is not true. Don't ask me any plasma physics questions. So, I mean, people who care about this stuff care about the distinction between stirring and mixing. And if you're not familiar with the topic, it's something that you may not have encountered before, that there's a real distinction between what we mean by stirring and what we mean by mixing, though, in fact, sometimes the boundary between the two is more gray. Stirring, the way I like to think of it, is the cause and effect. So stirring is the cause, and mixing is the effect. Okay? So you can have mixing with no stirring. We'll talk about this a little bit later, but you have pure molecular diffusion. You put some blob of heat in some water, and you wait for the little disturbance of heat to spread. At the end, you would have a mixed system because it would be homogeneous in some sense, but it would require no mechanical action on your part. So stirring is the fact that you're going to use a spoon, say, to stir your system. Okay? And you can study stirring by itself with never invoking molecular diffusion whatsoever, or molecular processes. And but to study mixing, though, you do need to invoke molecular processes or something like them, as we'll talk in a bit. And stirring also is related to a slightly different thing, which is called transport. And transport has to do more about carrying stuff from one place to another without necessarily trying to mix it in place. So a typical transport question would be, for instance, what is the flux of heat across the Gulf Stream in the ocean? Okay, because you're not mixing anything, you're just asking, if I start with heat on one side and heat on the other, just how much of it actually manages to cross the Gulf Stream. Okay, so that would be a transport question more than a mixing or a stirring question. Again, all of this would contain sub-questions about stirring and mixing, but for us, we're going to try to keep these things rather separate. And I'll talk about transport a little bit. So the quantity of interest will usually be some concentration field, which we denote theta. I'm not sure why I don't use temperature, actually. I don't use capital T. I mean, theta is often a temperature anomaly, right? It's often the deviation from some reference temperature. But I don't know. I've gotten used to using theta as my temperature. But substitute whatever you want, right? It could be temperature. It could be the concentration of some solute, like, for instance, chlorophyll is an interesting scalar to look at if you're an oceanographer, because you can see chlorophyll from satellites. And so it's a very useful tracer because you have these beautiful maps of chlorophyll across the ocean. That's a very nice scalar. But for me, I'm going to be talking about passive scalars. Passive scalars is when the scalar is assumed to have no buoyancy. So temperature, of course, does have a buoyancy. I mean, it makes water lighter. Salinity is another scalar, and it makes water heavier. So those are interesting things, but I'm going to neglect the feedback on the flow for these lectures. So what we're going to be talking about is essentially what's called kinematics. You assume some stirring mechanism, but your passive scalar does not react back onto the flow. So again, This could be temperature, aka heat, right? I mean, it's really heat, not temperature, of course. You multiply by the heat capacity to relate the two. Could be chlorophyll. It could be, you know, ozone. What's ozone, O3 or O4? It's 3, right? Okay, good. All sorts of things like that that are carried along by the atmosphere or the ocean, or something else, by the way, right? I mean, another interesting tracer might be radioactive isotopes in the Earth's mantle, for instance, right? They get moved around by the core flow, and you might not want to know where they end up. So there's all sorts of geophysical problems with passive scalars or active scalars being moved around. So let me use little underbars for my vectors. So as I said, the viewpoint that we take is that the velocity field, the stirring velocity field, or the mechanical action, that's the spoon, is given, okay? As opposed to derived from some fundamental equations like Navier-Stokes or... So usually, again, if you couple the temperature field to the velocity field, you get what's called the Rayleigh-Bénard system, which tells you about how buoyancy moves in the ocean. And you can study this, and people have, and I have, but it makes things a lot harder, as you might imagine. And it's true that actually you don't learn as much as you might think by considering the feedback of the passive scalar onto the velocity. So given these two quantities, oh, by the way, of course, we're going to be usually assuming that we're dealing with incompressible fluid here, just because that's true of air and water for the most part. Of course, the deviations can be important, but also because it makes all the math much nicer. So let's keep that around for all of the lectures. And it's going to be in some domain omega. And I will often refer to, again, I'm sorry, I don't know the background of people at all at this first lecture, but maybe I'll point out sometimes the difference in notation between mathematicians and physicists, because that might be useful. So mathematicians like to use little squiggly omega for the boundary of a region, whereas if you're a physicist, you would say, you know, V and S for the bounding region. But mathematicians love the little squiggly symbol. I'm sorry, I hope I don't insult anybody by doing, I guess I just don't know. I'm assuming that most people here, who's an applied mathematician? There's not many of, well, a few. Most people are ashamed to admit it. Who's a physicist? Okay. Who's something else? Okay. What's the something else? Engineering. Huh. That's where you make things. I see. That's nice. What flavor of engineering? Aerospace engineering. Okay. Oh, that's good. Okay, so that mixing, of course, in aerospace, that's a good, you know. Aerospace engineering, I guess, of course, mixing. Actually, a relatively mixing poor field. I mean, unless you take combustion as being part of aerospace engineering. Huh. You can leave if you want. I've just advertised that every single, you know, field has a mixing problem, but aerospace engineering doesn't have that many now that I think of it. All right. So we need some boundary, oh yeah, so what's the equation? The master equation for mixing is the famous advection diffusion equation, and I will use kappa as my diffusivity. So again, this is called the advection diffusion equation. Sorry? Yes, that's right. So yeah, U is completely specified in omega. Yeah. If you look in some older books, it's often called the convection diffusion equation. That terminology was current for a long time, but I think in the modern way we've separated now convection to mean really when there's buoyancy involved, from advection, which just means motion of fluid due to a velocity field. But again, you will often find disagreements about this. It's by no means a universal relation. This is what's called the diffusivity. Or the diffusion constant, goes by some other names. And this is our friend the Laplacian, again to point out the difference between math and physics. Mathematicians love using delta for the Laplacian because, of course, it's so difficult to write, nabla squared that the pure mathematicians are incapable of doing it, so they define another operator. To be honest, I wish they'd at least define it as minus, that delta is minus del squared, because then it would be what's called a positive definite operator, and you would at least have one mild piece of reasoning for introducing new notation. But they don't even put the minus sign there. Who's a pure mathematician here? Oh, thank God. Whew. Dodged one. I'm going to, in my head, compute the probability that a pure mathematician is going to look at my lecture. Done. Okay. It's... It's what's called beyond all order asymptotics. Okay. So, of course, when somebody gives you a partial differential equation, I like to tell my students, any idiot can solve a partial differential equation. It's the boundary conditions that kill you, right? In the sense that we have all these wonderful partial differential equations, especially linear ones, right, where we know the absolute general solution to these equations. We can write down some kind of closed form solution, but it's nearly useless because you haven't applied boundary conditions. Boundary conditions are the real killer. And there are two types here, but I'm going to focus on one particular. So there's going to be a normal, an outward normal to our boundary, and the kind of traditional boundary condition is to say that the normal gradients, the normal derivative of the concentration is 0 across the boundary. So this is the so-called, well, let me put another one. This goes as well with the requirement that n cross u, n dot u itself is 0. And this is on the boundary of the region. So in other words, the second thing is usually called the no penetration condition, the fact that there is no flow through the boundary itself. So in other words, the velocity field near the edge of my domain is not allowed to have a component through the domain. Okay? And given that, I can then require that the concentration itself have a normal gradient condition like this. Okay? And this means essentially that my passive scale, this is what's called an insulating boundary condition. So it means that heat does not flow out of my system. Okay? You can see this way if you write this equation in so-called conservative form. Oh, by the way, here's a useful vector identity. The div of u times theta is u dot grad theta plus theta div u, but div u is 0. So therefore, we can move u dot grad theta in and out of the divergence, and so we can rewrite this equation as minus the div of u minus kappa grad theta. Okay. And then this is the so-called conservative form of the heat equation, or of the advection diffusion equation. And it says that the change in theta is minus the divergence of this vector, and this vector is called a flux vector. And so essentially our boundary conditions are saying that there is no flux to the boundary because the flux vector dotted with the normal is 0. But it's 0 in a very, this is stronger, right? I'm requiring each part of the flux vector to vanish separately. That's only because physically it makes sense to impose the fact that there's no flow through the boundary. Though you can relax this, right? So there's something called the suction boundary condition, where you have a surface and you're sucking fluid through the surface with little holes. In fact, this is used a lot in aeronautics for control problems. For trying to control turbulent boundary layers, you apply some suction. In that case, you would not be able to claim that things are conserved in this way, right? Because you're losing fluid. But here we're going to assume that everything is nice and bounded. In fact, our domain is also going to be infinite sometimes, in which case you definitely do conserve things. Okay? Please feel free to interrupt me with questions. Okay. What am I missing? Oh yeah, there's a theta here, thank you. U times theta. Yeah. The density? Yeah. That's what I'm saying. That's what I, yeah. So the question is whether the time of evolution of U depends on theta, and it absolutely does in general, but you can also neglect this, right? I mean, you can, it's important if you're in a situation where you're convectively unstable or something like this, right? But in many cases, it actually doesn't matter very much that the temperature changes the density of water a little bit. Or think of theta, the temperature being actually like chlorophyll or something, in which case it's quite passive. Even though it makes water a little heavier, its density is not important enough to cause convection. So there are many, many cases where you can consider them to be, where you consider U to be decoupled from theta, which is the limit we'll take here. But you're absolutely right that in many other situations, that is the interesting part, the fact that they're coupled. But we're not going to be in that situation here. We're not going to solve Navier-Stokes because we're not that ambitious. Exactly. Exactly. Sorry? Sorry? Where's the source term? There can be, yes, absolutely. Yeah, in fact, I will put one later, but you can also have a source. You can add some forcing, some extra term that tells you that your domain itself has hot and cool spots, okay? And this is what's called body sources, because actually most of the time when people deal with convection problems, they put sources at the boundaries. You say that you're heating from below or something like that. But there's some problems where it's actually internal heating, where you... In this case, this is going to be an initial value problem. So there's no source. What you do is it's the coffee cup problem or the teacup problem, right? There will eventually be a uniform temperature, right? Yeah. So maybe I'll talk about this a little bit, but you're right, we're getting closer to asking what is exactly the mixing question that we're asking, right? And what I'm formulating right now is the classical initial value problem question of, I give you some initial condition with a temperature disturbance, and I ask you, how long does it take for it to relax to some uniform state? Okay? So that's a mixing problem, but it's not the only mixing problem in the sense that it's the one that's, yeah. If you have sources and sinks and you keep inputting stuff, there's other ways you can characterize mixing. But in our case, we're going to ask the initial value problem. So closed container, put some dye in it, stir, and ask how close you get to uniformity over time. Okay? What is? Chlorophyll, yes. Yeah, that's right. It's well, it comes from the phytoplankton. It's not the chlorophyll itself is not dissolved. It's the fact that there's phytoplankton that you can observe. Yeah. Maybe in the next lecture I'll bring some satellite pictures of this. It's quite beautiful. You can really visualize a lot of flow in the ocean by just using chlorophyll. What I'm saying is that, yes, the chlorophyll is being carried by an organism, but the satellite sees the chlorophyll. There's something about the way waves scatter that allows you to see chlorophyll. Don't ask me about the details. Okay. But also, if you push a bit hard, you'll find that I know very little often about these actual applications, right? So don't push too hard. Okay. All right. Is there another comment? No? Okay. So let me define the angle operator, the angle brackets, to be a volume average. Actually, why do I have an average here? Do I want an average? So I'm trying to decide whether I want an average or I'll take an average. So again, this is a mathematician's notation where you say that the volume of a space is written as the absolute value of that space. So here, omega is the volume of omega. Okay, and this dot just denotes the fact that if I put a function here, I have to reproduce the function in here. Okay, So it's just a shorthand for saying that this could take any function as an argument or even a vector or something like that. So this is the averaging operator, the spatially averaging operator. And it's a really nice building block for all this because it allows you to start to derive some actual nice mathematical consequences from the advection diffusion equation. So let me label this equation AD for advection diffusion. So let's derive some physical consequences or mathematical consequences of the advection diffusion equation. Let me multiply the whole equation by m theta to the m minus 1, where m is some constant. Okay. And so then, let me do the actual calculation. And I'm going to use the shorthand here for time derivatives as, a lot of my derivatives I'm not going to write as denominators, I'll just write as dt. I'm sure most of you know that notation. And I'll switch back and forth between the notations for, not the notation, but the expression for this middle term here, right? Often I'll write it as u dot grad, other times I'll write it as div of u theta. Because div u is 0, it doesn't matter. And then this is going to be m theta m minus 1 Laplacian of theta. Okay. So I'm going to go fast here on what I'm going to derive, just because of time constraints. Sorry? Did I miss kappa again? Yeah, I'm gonna miss things like that. Thank you. Kappa is still there. And so now the key is now to average, meaning to take the averaging operator of this equation. Okay, so I take my angle brackets and I apply it to both sides of this equation. I'm going to take kappa to be constant, by the way. You don't have to take kappa to be constant. But if kappa is not constant, you have to rewrite the equation differently, right? So the generalization of this equation can be generalized in two ways. So a more general form of this term is div of tensor D, where D is a 3x3 matrix, which could depend on space, right, times grad theta. And there's a matrix product there. So in the absolute most general case, you could have a fully tensorial diffusion tensor as opposed to a diffusion constant, which also depends on space. Okay, but in fluids, this happens less because fluids, of course, are moving, and so it doesn't make so much sense to think of the diffusivity to depend on space, though there are circumstances where, especially when you model diffusivities as turbulent diffusivities, there definitely are times where you want D to be a tensor or to be a function of space. But we're going to assume here essentially that this tensor is a diagonal matrix with a constant diffusivity, so you can pull it out. I just wanted to mention that it's possible for this to be a tensorial equation. Okay, so the averaging here, there's a trick that you can use twice here, which is that if I have theta m minus 1 dt theta, that is d dt of theta to the m averaged. Because the d dt travels through the averaging operator. By the way, what's the circumstance in which d dt would not commute with the averaging operator? Can you come up with a quick example? Yeah, moving boundary, right? If the boundary of the region itself moves in time, exactly. That is essentially the only case where you're not allowed to commute d dt with the integral. Probably if there's some weird discontinuity also, you might run into some problems, but overall, that's really the main event. And by the way, this operation only uses the fact that d dt is a derivative, so it also works for u dot grad, because u dot grad is just a derivative. So it is also true that m theta m minus 1 u dot grad theta is average of u dot grad theta to the m. Again, because u dot grad acts exactly like a derivative. So the only property I'm using here is the fact that the derivative of theta to the m is m theta m minus 1. But then by the chain rule, I have to then take a dt of the quantity. So the left-hand side, I'm kind of done now. And now I'm going to attack the right-hand side of this equation. So let's see. I'm sure I could do it, but let me not. Let me make sure I don't make any mistakes. So what you want to do is our old friend integration by parts. So this is div of grad theta, so I can integrate it once and write this as div of theta m minus 1 times grad theta minus grad of theta to the m minus 1 dotted with grad theta. So again, that's just integration by parts on the divergence operator. Oh, sorry, I forgot to say the most important thing, which is here, this is div of u theta m, right? Again, because of the same, this equation works even if you put an m here, right? Because it doesn't matter, theta m is the function now instead of theta. And so I can reverse, I can bring the divergence outside here, and then I can use the divergence theorem to write this as an integral over the boundary. There's a volume factor of theta m u dot n hat ds. Again, by the divergence theorem. And then this is, of course, 0. Okay? Because u dot n is 0 everywhere on the boundary. Okay, so I've just used this second property here as part of my boundary conditions. Okay, so the average of the second term vanishes, and you'll see that happens all the time in transport equations, that somehow this advection term does not actually contribute to total change in a lot of quantities. At least it doesn't contribute directly, and that's what we'll see in a second. Question? Sorry, I'd forgotten to say this. Because now I'm going to use this here as well, right? This is going to be m over omega integral over s theta m minus 1 grad theta dot n ds minus, well, let me just comment on this term first. So again, this is this term. It's a perfect divergence, so I can use the divergence theorem to write it as, or Gauss's theorem, depending on how you learned it when you took calculus, going from here to here. But notice now I've got a grad theta dot n, and again, that is 0 according to my boundary conditions. So this is 0, and therefore the whole integral will be 0. And I'm left with this other term, but I will integrate this term by parts again. So I really want to move all my derivatives off of the theta term. Sorry. No. Sorry, I don't want to write, no. Let me just expand this out is what I'm going to do. So I have an m from here, and then grad of theta m minus 1 is m minus 1 grad theta times theta to the m minus 2. And then I still have another grad theta. And then I need some averaging brackets. Okay? And so that's it. Now I can put it all together. I can use this and this to write that the time derivative of the average of theta to the m is minus kappa m minus 1 average of theta m minus 2 multiplied by the magnitude of grad theta. Okay? For any m. Okay, questions so far before we talk about the interpretation of this equation? So there's clearly two. Immediately, if we think of now as m being an integer, which it doesn't have to be, but the interesting cases, well, let's focus on the integer cases first. There's clearly two cases that do something special, right? M equals 0 and m equals 1 have a special property. Well, m equals 0, it's not super interesting, right? It's just saying that if I take m equals 0 here, then I get 1. So it's saying that the time derivative of 1 is 0. Okay, so m equals 0 is boring. It just says that, the time derivative of a constant is 0. Okay. By the way, the kind of calculations here I'm doing are known as formal calculations in mathematics, meaning probably a serious guy like Georg would probably prove first that all these things exist before actually starting to claim that you can manipulate this equation. But I'm sure none of you are the sort of people that care about such things. But a real mathematician would not have made it this far during this lecture. A real mathematician would probably be at the first 10th of the board, right, and trying to prove that the letter X exists. Sorry. This is going to be recorded. Oh, yeah. So for m equals 1, we also get this. And now that's interesting, right? So it's something that you could probably have guessed. It says that the time derivative of the average of theta is conserved. Okay? And by the way here, you can almost always commute average with total quantity of. There's a question of normalization, and that's what I was pondering when I was looking at my notes. Sometimes I put a 1 over volume here, sometimes I don't, right? And it depends on how I feel on the particular day that I start doing a calculation. So when I say average, I'll often say total quantity of, because it's all the same up to some constant. If you take omega, the volume of omega to infinity, then this starts to matter in an annoying way. So later on I will deal with infinite volumes, and then we can't take this averaging operator because, on any volume, the average quantity is usually 0 unless things are infinite, right? So, okay. So that's not surprising, but it's important, right? It's really because we built it into our boundary conditions. And we could have gotten away with less, but we put a very strong case here that both of these things vanish. It would have been okay for just the sum of these two things to vanish, well, with a kappa in there, or the difference of these two things with a kappa, right? We could have said that this vanishes with normal derivatives on the boundary, and that would have been enough. But again, the physical boundary condition is even better than that usually, because it does say that these two things should vanish separately. Well, my point is that the fact that these boundary conditions are applied means that the passive scalar is not allowed to travel in and out of your domain, and so therefore you would expect the total quantity to be conserved. M equals 2 is probably the first interesting one. Let's see. It's going to be a 2. There it is. Yes. There is?
For m equal to 1.
Oh, yes. So this is where... No, well, okay. So Amit is asking, if I put m equals to 1, I get a 1 over theta, and do I have to worry about things where theta is 0, right? Do I have to worry about singularities? The answer is you don't really, because this is one of those cases where if m is equal to 1, I should probably not get that far. I should probably start again, right? And then I will see that I never need to divide by theta actually, right? That it's a figment of the particular derivation. But that's a good point. There could be situations where that looks funny, but in this case, it's perfectly fine. If you imagine putting m equals 1 ab initio, right, from all the way from here, then there is no issue with dividing by theta. But that's a good point. In other words, I don't need to do this integration by parts. Exactly. Yeah, exactly. Okay, so this is the first kind of important equation of this case. Well, they're both, both of these are important. in their own way. But the second one is the one that has at least some content about what mixing is all about. So what does it say about mixing? Well, the important thing about the thing on the left is that it's positive, or it's non-negative, right? So the average of the squared of a quantity, of course, is non-negative. So this is some measure of, so this is how much concentration I have in there, but this is a measure of its fluctuations. In fact, there's an interesting quantity called the variance of theta, and the variance of theta is merely, it's what you would get if you were a statistician or a probabilist, and you treated theta like a probability density. And oceanographers and all sorts of people call this the variance. It really isn't a variance necessarily, because theta doesn't have to be a probability function, right? But people always refer to it as the variance anyways. And the variance is the average of theta squared minus the average of theta squared, just like it is in statistics. Okay? And this quantity is very useful because it tells you about the fluctuations in the concentration field. Because it tells you how much excursions away from the mean you see when you look at the concentration field, right? So if theta is a constant function, then it must be equal to its mean, and so therefore this is 0. And if theta is it doesn't have to be just oscillatory, but if it has large fluctuations away from the mean, then this thing will tend to be big. And this is non-negative, by the way, right? So this is bigger or equal to 0. So the fact that so in fact I can couple together these two equations because this is actually constant. And so if I take the derivative of the variance, I get the same equation again. Right? Meaning that the time derivative of the variance is the same as the time derivative of the squared integral. So I'm just not talking about it because I'm not talking about it, basically, right? I mean, there could be something interesting to be said about that, but I don't have anything to say right now about it. I mean, it's also because you choose to focus on a certain power of theta because it tells you something interesting about the concentration field. And here it is clear from the right-hand side that m equals 0 and m equals 1 are actually very special cases. It's also true that, if you believe in the, if you believe that a nice way to learn about a distribution is to take its moments, right? But its integer moments, if things are nice and smooth, contain the information that you really want. You don't actually have to look at the fractional moments typically to discover anything interesting. So the short answer is just because those are the most interesting ones, I think. But you could certainly look at fractional moments if you wanted to. They just have horrible equations, basically, right? Because you get, well, it's not that bad. You just get fractional powers of your theta. But if your theta is negative, then you've got some issues, right? Which it can be at this point. So it's not uninteresting to look at fractional powers. It's just a lot harder. So let me just first tell you about what this equation is saying. I claim that this equation, the boxed equation, and let me box up this one as well, and let me double box it. That means super extra interesting. This equation in a way tells you everything you need to know about stirring and mixing, to some degree. Because let's talk about time here. And let's write the variance. And let's think of the limit where kappa is small. Now, again, if you're a physicist, you should never accept somebody telling you that a dimensional quantity is small, because that doesn't really make any sense. But just accept it for now. Suspend your physicistness for a few seconds and just admit that we have this physical constant. I'm just going to assume it's negligible in some sense. Yes? Well, that's what I'm going to talk about right now. Yeah, exactly. That's what I'm going to plot right now, because if you look at the time derivative, if the variance is, if the diffusivity is small, then as was just, well, then you can neglect the right-hand side here. Okay, and that means that the variance is conserved. So if I look at a graph of the time evolution of my variance, it will start out at a plateau, right? Because initially, there is no reason why the right-hand side of this equation should be large, with some reasonable initial condition and some small value of the diffusivity. Okay? But of course, nothing would ever happen if that was the case. And so this brings us to a striking observation, is that this equation has no velocity in it. So it's not telling me anything about stirring in some sense, right? So I have no way of knowing. It's not a closed equation for theta, right? Or for the moments of theta, because the moment of theta squared depends on the moment of grad theta. So I really can't say anything about the evolution of theta squared. But let's, inject some foresight into how things are going to happen. The role of stirring, the role of the mechanical action, is actually to increase the gradients of theta. Because, you've all observed this when you stir in your, I notice here at the cafeteria that they already put the milk in the coffee, so it's not such a great example. But if you do add a little blob of cream to a coffee, of course, you know that it makes filaments, right? So the evolution of mixing is usually to start with a blob, and the word blob is used all over the place in this field, so it's the technical term blob. And then as you stir it, it starts to stretch. But then if you stir it further, your blob starts to filament. That's what the mechanical action of stirring does, as we've all observed. But filamentation is another way of saying that if you imagine that your blob is, value 1 of the concentration, if this is 1 and this is 0, then if you look here, this becomes 0, 1, 0, 1, 0, 1, 0, 1. This is not a great example because I want to talk about gradients, and it's not going to work if I think of it as being 0 and 1. But up to some smoothing, you might imagine now that the concentration gradients are becoming quite large because the function needs to switch from light to dark very rapidly. And so that means that grad theta is getting large. But this equation also tells us how large it's likely to get. Because if grad theta becomes of order, if grad theta squared becomes of order kappa, then the right-hand side becomes important. Okay? So in other words, there is some point here where the gradients are of order kappa to the minus a half, where the right-hand side becomes important, and then this function has to decrease. By the way, this is non-positive, right? So this always has to be less than or equal to 0. And that's the key to understanding, basically, all of stirring and mixing, is that the role of stirring is merely to create gradients and to create enough gradients that they can overcome some small diffusivity. Okay, so you start out with a small diffusion constant, and the reason I say a small diffusion constant is because that's usually the geophysically relevant regime. It's very rare that you have a large constant of diffusion when talking about geophysical situations. It's also a bit of a tautology in the sense that if the diffusion constant is not small, then why am I doing this? Things are going to mix just by waiting a few minutes, right? So it's also that the study of mixing makes most sense when kappa is small. So when kappa is small, the role of stirring is to amplify gradients until they reach a scale proportional to kappa to the minus a half, but then they're going to stop increasing. That's an interesting point. This equation, the right-hand side now becomes of order 1, or of order minus 1 if you want, and this thing starts to decrease. And you could imagine that the gradients would keep increasing indefinitely, but in fact, they kind of settle down at roughly this scale, okay? Basically because the time dependence now, you are starting to suppress the variance, so you are starting to suppress the fluctuations. And so you enter a regime where advection and diffusion are balanced. And that is exactly when the gradients of order kappa to minus a half. And so then this proceeds like this, and then typically you get some asymptote to 0. You can't go to 0 in finite time if things are nice and smooth. Though there are some cases where you can go to 0 in finite time, as was proved by there's actually a lot of activity now by the analysis people, and it's been recently proved rigorously it's possible for this thing to go to 0 in finite time. But it's kind of in a boring, it has nothing to do with physics. And you have to break smoothness. You have to do something completely crazy. Otherwise, the existence and uniqueness theorem tells you you can't do it. Okay? So that's a kind of the rough scenario for mixing. Sorry? Delta theta? Yes, exactly. So, I mean, I haven't shown this. I'm not trying to say that that's obvious, right? But what I'm saying is that the role of stirring, see, this equation doesn't see stirring directly, right? And even if there's no stirring, things will decay. I'm not trying to say that stirring is the only way that this will decay, right? If I give you the diffusion equation, so if I set the velocity to 0, then you get exactly the same equation there, and the concentration will relax. So there is a grad theta, right? But there's nothing to amplify grad theta if there's no stirring. Grad theta has to stay at whatever, if you put a blob, a Gaussian initial condition, and you don't have any stirring, then the gradients will remain at the same order as what you put them in, and then they will become smaller over time. And so this equation will decay at a rate dictated by kappa. Whereas if you have stirring overcomes the kappa that you have, however small it is, and then things then decay at a rate which is often independent of kappa. But that's actually a surprising fact, right? Another interesting fact about this equation is because you have to wait until this happens, you have this funny feature that often the rate at which this happens is actually independent now of kappa. Okay? It's a singular limit, meaning the limit as kappa goes to 0 is actually independent of kappa. Okay? But that's not for every flow. I'm just saying there's some flows that have that property, and those are the best mixing flows in a way. The ones that don't actually care about what value of diffusion has. Now you might say, how is this possible, that it's independent of diffusivity? Well, it's not, because the time it takes for you to reach that stage depends on the diffusivity. But once you reach that mixing stage, then things are independent of diffusivity. In other words, you have to build up large gradients, but once you've built up the large gradients, things relax at a standard rate. Okay. Minutes. I'm doing pretty good, actually. Okay. So this regime, by the way, is what I would call the chaotic mixing scenario. It turns out that the process required to amplify the gradients to that degree requires some particular properties of the velocity field which are associated with what's called chaotic advection. And I'll give some examples of this sort of thing in the next lectures. But again, this is managing to build up the gradients of the order kappa to minus a half is the ideal case in some sense. Okay, it's when mixing works best, and then the chaotic mixing scenario is when this is independent of kappa. And it's the ideal, in the sense it's what you'd like to achieve when you're mixing. Yes, I mean, it's not even that late, actually. You're saying here? Yeah, so it's not necessarily very late. So as we'll see, the time here, the key fact is that in the right chaotic mixing scenario, the time until which that's an important point. I'm glad you raised it. The key fact is if things are working for you, if you've got the right kind of mixing setup, the constant that determines how long you have to wait until things become in this decaying region is only logarithmic in kappa. And that's what allows me to say that kappa doesn't matter in a way. is that kappa may be very small, but if I multiply kappa by 10, I only have to stir just a little bit longer to get the same result. Okay? So that's what makes, that's what makes the magic of you, when let me put it this way, right? If I somehow give you two types of cream with slightly different mixing properties, do you expect it would make it harder to mix your tea? It wouldn't really, right? A few quick flicks of the spoon is all you need to mix, almost no matter what you've put in there. And that's kind of this statement that, the properties of the thing that you put in there are only logarithmic in the diffusion constant. Now, you're going to say, sugar is harder to mix partly because it's made of suspended particles and actually has to be dissolved. That's a completely different phenomenon, right? There's some aspect of mixing in this, but that's not the same as what I'm talking about here. Questions? Yeah. That's right. It's logarithmic in kappa. Sorry? That's right. So the only thing that depends on kappa are the initial details here and this time. But after that, and the concentration field itself will depend on kappa. Okay? So in other words, when you look at the variance, this rate here doesn't depend on kappa. But if you look at the concentration, right, if you look at your filaments, the typical width of the filaments is of order 1 over square root of kappa. Okay? The typical width is order root kappa. So the actual concentration field depends on kappa. The smaller you make the kappa, the more fine structures you're allowed to have. But that's not contradictory with the fact that the rate is independent of kappa. Yeah. Yes? Viscosity, so they just diffuse different things. Viscosity is the diffusion of momentum in a flow, right? But a priori, they're completely unrelated. So, if you put heat in a fluid, again, let's assume no motion, then it will diffuse at a certain rate, whereas momentum also diffuses at a separate rate, and the two are not the same. In fact, that's the ratio of the two is called the Prandtl number. It's 7 for water. So viscosity diffuses faster than temperature, typically in water. Right, so perhaps you've seen this definition. So the Prandtl number is the viscosity of water over the heat diffusivity in water, and that's about 7 for water. Okay, which means that the diffusion constant for momentum is about 10 times larger than for temperature. I've got a lot of friends who study this, and it turns out in the world, the smallest Prandtl number you can get is 0.002, I think. Liquid sodium is the smallest Prandtl number over all known materials. And the largest one, I think, is astronomical. You look like you have something to say. No, it's just your usual face. I see. Okay. Okay. So to wrap it up then, let me make that point, maybe drive the point home. Again, as I said, this is kind of the introductory lecture. So let me finish by giving you a quick calculation that tells you why you need mixing. And also, I've been a bit cavalier about the dimensions of kappa. So let's get into the details a little bit more about kappa. So for the diffusion of heat in air is given by a constant kappa, which is 2.2160 times 10 to the minus 5 meters squared per second at 300 kelvins. So it may not surprise you that, in fact, the diffusion constant depends on temperature, as do all physical quantities, but we usually neglect that dependence when you're focusing on a narrow temperature range. Again, so, there may be reasons why you don't want to assume that, but it's often the case that you just assume these things are constant. So let's assume that the diffusivity is constant. So this is the value of the diffusion constant in air. Notice, by the way, it always has units of length squared over time. All diffusion constants have units of length squared over time, basically because the advection diffusion equation is linear in what you're transporting. And so the units of theta never come in, right? You never see the units of the thing that you're mixing in this linear equation. So the only thing that matters is the units of the diffusivity, and according to this equation, it's length squared over time. Okay? So here's an interesting calculation. I'm going to say that this room is 10 meters long. Okay? That's probably, is that fairly close? Maybe it's probably a bit more than that, but not much more than that. Maybe 15, exactly. So the question is, how long, let's say that I put a source of heat over there, how long until the heat manages to propagate on the other side of the room? So this is going to appeal to the physicists in the room, right? Because we can just do a dimensional analysis calculation. So if I have a room which is 10 meters, okay, then the time of propagation across the room is just the dimensional analysis length, time that you'll get from this, right? Because there's only one, if I give you a diffusion constant and a length, there's only one way you can create a time out of this. So the time has to go as L squared over kappa, right? Because kappa is an inverse time, but it has two lengths in it. And that's 100 meters squared over 2 times 10 to the minus 5 meters squared per second, which is 50, let's see, 50 times 10 to the 5, which is, I guess, 5 times 10 to the 6 seconds, which is about 50 days. Okay. In other words, the back of the envelope calculation for diffusion of heat across the room says that if you were trying to heat this room or cool it, right, you would have to come a month and a half before the lecture, turn on the space heater, then, everybody leaves, but then you come back, and now the room is at a good temperature, right? So this is clearly nonsense, of course. Okay? And it's a great example of how dramatic the enhancement of diffusion by stirring is, right? The reason why, of course, this isn't true is because even me moving around the room creates a little air current, right? And that air current is vastly better at transporting heat across the room than is any molecular diffusion. So it's that. Well, of course, we have fans going, right? There's an air filtering system. Also, natural heat convection in the room is also helping move the air around. But the point is that all of that completely dominates the molecular values. Of course, in geophysics, this is well known, right? Nobody ever uses the molecular value of viscosity or diffusivity when computing things having to do with planet Earth or something, right? I mean, it's so many scales down the line. But I guess I just wanted to point out for the very end like this that even in a trivial problem like this, right, of how to heat a room, it really is all about stirring and mixing. There is almost no contribution directly from just heat conduction alone. And so we'll see in the next lectures, what I plan to do is to show you some models of stirring flow that kind of realize this vision to some degree. Yes? Sorry, I can't hear you very well. There's a lot of... Yeah. Absolutely. So this is what's called the dimensional analysis argument, meaning it's true. If I put a temperature of... If I take the sun, right, and I bring it to the corner of the room, then of course the room is probably going to heat up pretty fast, even through conduction, right? So if you make the temperature gradient large enough, then it's going to work. But this is dimensional analysis, so the assumption is assuming that everything else is kind of reasonable. And it is, right? When we say a room is cold, it's because it's 260 kelvins as opposed to, but we want a 270 kelvins, right? So the gradients in terms of absolute temperatures are not that large. But you're perfectly right, of course. And that, are you a physicist or yeah, so physicists, use dimensional analysis all the time, but you have to also be aware that dimensional analysis is not an absolute thing, right? It's possible to break dimensional analysis by making some extreme assumptions. Absolutely. Yeah, well, of course, if the sun was in the corner of the room, probably I would have to take into account the temperature dependence of diffusivity in air. I would probably have other problems though, right? You have to admit. The atmosphere would get vaporized immediately, so there would be no air, right? So it would be just bad news altogether. All right, thank you very much. That's it. You don't have to clap. Do you usually clap? Okay. I know, but I was just, the way I finished, I suddenly realized that I was finishing the way I was expecting people to like, to clap, right? But, so,
Sorry to break your expectations.
I didn't want to, no, but I suddenly realized, no, you don't have to, you know, just. See, now I've made it weird, you know?